So now that we derived the equation for the acceleration for the hanging block problem, we can actually use the equation in an actual problem to find the acceleration. So this is the equation we came up with in the last video. So let's substitute some numbers in. Let's just say that the hanging block has a mass of 1/2 kilogram, and the block on the table has a mass of 2 kilograms. So to find the acceleration of this block here, it's going to be equal to, I'll plug numbers in, 0.5 divided by 0.5 plus 2.5, which is 2.5, times g. So 0.5 divided by 2.5 is equal to 0.2. So it's equal to 0.2 times g, which is about 2 meters per second squared. So in this problem here, this block will accelerate to the right at 2 meters per second squared, and that one will accelerate down at 2 meters per second squared, or you could say it would have an acceleration of -2 meters per second squared. On the homework, the next homework, homework 4, there'll be some problems, I believe, where you make one of these get small and another one get really big. And let me just do a thought problem like that with you, and then we'll move on to the next problem. That's the Atwood machine problem. So let's just say that this block got really small, and this one got really big. So that could be approaching 0, that could be approaching some number like 100 kilograms, let's just say. So let's just say this got really small, and this got really big. Well, this ratio here, if this is a small number plus a really big number, this is going to look approximately like, so if mh is much, much larger than mt, then what you have up here is going to start looking like acceleration is equal to, well, this approaches mh. If this is much smaller than that, then adding something really small to something really big is about equal to that same really big thing. So it's equal to approximately the hanging object divided by the hanging object, mass, times g, which is about equal to g. So what that means is when this object gets really small and that one gets really big, that one's going to accelerate to the right with an acceleration of about g. That one's going to accelerate down with an acceleration of about g. In other words, it's going to be as if it were in free fall. Now let's look at the other extreme of making this one really big and that one really small. Let's see what happens when I do that. So if the block on the table is really big and the hanging block is really small, then what's going to happen here, if this is really small, it would start looking like 0. And if this is really big plus something really small, it would look like that thing that's really big. So this would approximately be equal to something that's close to 0 divided by mt plus 0 times g. In other words, it's going to be about equal to 0 when this gets much, much larger than that. You're going to have an extremely small acceleration. It's kind of like I used the example of if this were the Titanic and this were a mouse, how much would the mouse cause the Titanic to accelerate? Basically not at all. Neglecting friction even. Okay, so these are the extreme cases of what you can do with the hanging block problem. Now I'm going to stop the hanging block problem and I'm going to do another problem which looks something like the hanging block problem, but it's called the Atwood machine problem. The Atwood machine looks like this. You have a pulley, and from that pulley is suspended two masses. And I'll say that this is M1, this is M2. And of course, if they're the same size mass, you wouldn't expect any acceleration. But what if one is bigger than the other one? That's what we want to look at. So I want to use the same approach to solve this problem that we used to figure out what the acceleration would be for the hanging block problem. So the first step is to sketch all the forces that are acting on both masses. So this one is going to have a tension force. I'll call it tension force 1. This one will also have a tension force. I'll call that tension force 2. Similarly, this will have a gravitational pull. I'll call that Fg1. And I'll call this one here Fg2. those are the only forces I have to consider in this problem that I can see that are acting on either of these objects here. So now I'm going to apply Newton's second law. Remember, my goal is to find the acceleration of these masses. One of them would probably be positive, the other one would probably be negative, because one's going to accelerate up, the other one's going to accelerate down. All right, so if I apply Newton's second law, then I'm going to say, okay, let's just say for object 1, F net, this is object 1, not step 1, F net 1 equals M1A1. So I could say, okay, what are the forces acting on object 1? Well, I have object 1's tension minus object 1's gravity. So what I'll do is I'll say Ft1 minus Fg1 equals M1A. And for object 2, I can say Ft2 minus Fg2 equals M2A. So I just applied Newton's second law. This is the F net, by the way, for both cases. And this is the mass times its acceleration. So now what I'm going to do is I'm going to see what forces have to be the same. Now remember, this is the tension force around a pulley. So what I can say because of that is that Ft1 equals Ft2. I'll just call it Ft for short. So that's one thing I can say is true about this situation here. And the other thing that I can say is true is that one of the one's acceleration is going to be equal to the negative of the other one. So I could say that A1 equals minus A2. One of them I'd have to say is going to be the upward acceleration. That would be the smaller mass. The larger mass one would be a downward acceleration. So I'm just going to, for the sake of this argument, I'm going to say that M2 is larger than M1. So I could define which one's actually going to be positive and which one's going to be negative. Okay, I'm going to erase some of this text and then go through and find out what that acceleration is, just like I did for the hanging block problem. So I'm going to simplify these equations here. I'll say, okay, Ft minus Fg2 equals M2 times A. And I also have, Ft minus Fg2. This should be 1. Then I also have Ft minus Fg2 equals M2 times minus A. And I'm making this acceleration be negative because it's the bigger mass, so I know it's going to be a downward acceleration, whereas the other one is going to be an upward acceleration, but it's going to be at the same size, just opposite direction. So I'm going to simplify. I'll put this minus sign in front, and then I'm going to have to do a substitution. So I'll start by simplifying this one. I'll say, okay, Ft minus Fg2 equals minus M2 times A. All right. And then I'll write this one over here. I'll say Ft minus Fg1 equals M1A. So take your pick. I'm going to substitute out one of these tension forces so I can solve for acceleration. So I'll arbitrarily say I'll solve for this one. I'll say, okay, Ft, I'll add Fg1 to both sides. So Ft equals M1A plus Fg1. All right, so I solve this for Ft, and then I'm going to substitute this into there. All right, well, I should say into this Ft. Wherever I see an Ft up here, I will substitute this expression for that. So I'll come over here and finish this problem, and what I have is m1a plus fg1 minus fg2 equals minus m2a. And remember, fg1 equals m1g and fg2 equals m2g. All right, so I'll substitute these expressions in there, and I'll end up with things that are going to be easy to factor out. You'll see in just a minute. So I also want to bring m2a over to this side. So that's good. I'll do the substitution first. So I substituted my two FGs in, FG1 and FG2. Then I'm going to bring M2A over to this side. I'm going to bring both of these M1G and M2G over to the other side. All right, so if I move these to the other side, I'll subtract M1G, add M2G, and add M2A to both sides. All right, so do the same thing over here. So if I do all that, here's what I'll get. When I do all that, I'll get M1A plus M2A equals, I have M2G minus M1G. Hopefully you followed all that. All I did was I rearranged this equation to get the A's on one side and the G's on the other. Try that on your own. Make sure you got that. Then I'm going to solve for A. I'll factor out G over here. So I could say this is equal to G times M2 minus M1. And over here I have A times M1 plus M2. And I get A equals G times M2 minus M1 over M2 plus M1. That's my acceleration. Okay, so this is my acceleration for the Atwood machine. This is almost 13 minutes long. I'm going to stop this video, and I'll do another short video with some examples of how to apply the Atwood machine equation.